Okay, so today we will discuss hydrogen atom. We will discuss its wave functions, energies, and orbitals. I will not go through the derivation of the solutions. I am hoping all of you have done that in one or two other courses, and you can go through the derivations of the solutions of the differential equation in the book if you like. And I would actually strongly encourage you to do that. So, but I will focus on the problem and its solution and interpretation. In the last lecture, we actually discussed one extremely important thing, which was that if you can break down your Hamiltonian into terms that are functions of different coordinates, then the wave function can be written as, you know, the product of functions of those different variables. So essentially we can use separation of variables, and the total energy is just the sum of the corresponding energy terms, and our bigger problem is broken down into smaller problems for each of the term of the Hamiltonian. We will be using and exploiting that fact in many of the problems later on. Okay, so to discuss hydrogen-like atoms, let me start sharing my screen and review the hydrogen-like atoms. So let's start. So as always, you can stop me anytime, okay, for questions. So I'm writing review because I will not be going over the details, and I'm hoping that you can do it yourself. So a hydrogen atom is a nucleus with a single proton and electron around it. But a hydrogen-like atom is an ion with a nucleus of charge Ze, where Z is the number of protons and E is the charge of electron, and minus E charge on the electron. So you can think of examples as, for example, the Hamiltonian ion or lithium 2+ ion and so on. And perhaps also we can use some of these results approximately for situations where whenever we have some, you know, charge at the center and some charge which is, you know, at a distance from it, and we can use the similar analysis depending on the situation, if the charges are localized or if they are smeared out. If they are both localized or the distance between them is, you know, quite a lot, we can use the same treatment to analyze that. For example, the excitons that are formed by, you know, the electron hole pairs in semiconductor materials, they can essentially be treated like this, or maybe like two elementary particles of different charges that are existing in the vicinity of each other. Temporarily, they can also, you know, form a bound pair of negative positive charge. So that essentially becomes a hydrogen-like atom. So the treatment that, you know, we do for hydrogen like atoms, it's actually applicable in a host of situations where we have even if not the real, at least effective negative and positive charge present near each other. And if they're in the bound state, we can use the same mathematical analysis. But for now, we will use the terms and language as if we are treating atoms. And in the atoms, when we can, you know, think of hydrogen-like atoms where we have a nucleus, and it may not necessarily be a single proton. So it can have a charge equal to Z times the electron charge times the and the negative electron charge. Sorry, some alarm is going on. Let me check out if it's real or if it is some exercise. And I'll be back in a second. So please keep on logged in. Okay, so somebody is checking up, but we can continue in the meantime. Okay, so we can model many situations using the mathematical machinery that we will develop right now. So we have already constructed a differential equation. Did we or did we not? Okay, we can do it from scratch. Well, last time we were discussing that if we have two charges, one is at some position R1 and the other is at some position R2, we can break that problem into two parts. One is the center of charge motion. Okay. And the part which is related to the internal motion can be expressed in terms of the displacement vector from one charge to the another, and we can write the total energy of the system as sum of the center of mass motion energy term and the internal energy term. And for now, we will restrict ourselves to the internal energy term, assuming that the system as a whole is stationary. So for that, we will need the reduced mass. So reduced mass for this case would be mass of electron times the mass of nucleus divided by the mass of electron plus the mass of nucleus. And we will also need total mass, which is just the mass of electron plus mass of nucleus. And using this, we can write the Hamiltonian for the part of the internal motion as E square 2 mu plus the potential energy between the two charges. And the potential energy can be written using Coulombs law as minus Z E square 4 pi epsilon naught R. So this is 1 over R dependence. If I want to plot this potential energy as a function of R, this is something like this. So it's negative at R is equal to 0, and it goes down as R increases. Because of this negative sign, it starts from the bottom. This Z E square 4 pi epsilon is a constant and only dependence is 1 over R. Note that at R is equal to 0, this potential goes to infinity. That's an artifact present in the Coulombs law, and that's something that we will have to contend with. And this P square is the momentum term, which is minus iota h cut del square, which becomes minus h square del square over 2 mu plus V of R. So we can expand this del square in spherical coordinate, and it becomes partial square by partial R square plus 2 by R partial R 1 over R square partial square the theta square plus 1 over R square cotangent theta partial with partial theta plus 1 over R square sine square theta partial square by partial phi square and the potential term. Now, in this Hamiltonian, these are the terms that involve derivative with respect to R. So let's separate them out. And then if I multiply with minus h cut square 2 mu to the rest of terms and take this 1 over R square common, I get 1 over 2 mu r square, and this minus h cut square into all of the rest other than 1 over r square is actually nothing else but the L square operator, and our Hamiltonian is now expressed in terms of this part, which is the derivative with respect to r, and this part, which is which captures the derivative with respect to theta and phi, and this is the angular momentum square operator, and then this is the potential term. This L square operator actually has the eigen functions y, lm, theta, and phi, which are called spherical harmonics. And when this L square operates on this, it gives L into L plus 1, y, lm, and h square as well. And these eigen functions of this equation, if we use them here, we can express the total Hamiltonian of this problem as product of a function of r and spherical harmonic, because this L square commutes with the Hamiltonian, so we can write the total wave function as a product of the radial term and the spherical harmonic term, where the spherical harmonics satisfy this equation. And just a little bit more, these spherical harmonics happen to be the solutions of the eigenfunctions of LZ operators as well, which is minus iota h bar partial way partial phi, and they give minus, they give m h bar as the eigenvalue as well. So it means that this function, wave function psi, is an eigenfunction of the Hamiltonian operator. It's the eigenfunction of momentum square operator, and it's the eigenfunction of the z component of the angular momentum operator. I would strongly, urge you to go through the solution of this differential equation, because these YLMs, they are the product of associated Legendre equations and exponential iota m phi factor. So this YLM actually is a function like this. This is a normalization factor. This is associated Legendre equation, iota m phi. So the spherical harmonics have theta and phi dependence in the associated Legendre function, and then they have this complex part as exponential iota m phi. And actually, the imaginary part only comes up in this exponential factor in these spherical harmonics, and that's how it comes also in psi as well. So this, we'll see later on that even this function r is real and everything else is real except for this exponential part. Okay, so before I solve actually the hydrogen-like atom, let me briefly discuss the rigid rotor. So this rigid rotor is an approximation of two charges that are stuck at the end of something, you can imagine a rigid rod. So let's say this is positive charge and negative charge, and they are rotating, let's say, about the center of mass axis, an axis that passes through the center of mass. So maybe this is going around like this or going around like that. And actually, when we think about a gas, for example, let's say a gas of HCl. So this is like partially positive, partially negative. So we can imagine this molecule to be approximately a rigid rotor, because at low temperature, these vibrations are not much. So this distance remains fixed. And then this molecule is essentially a rigid rotor. Of course, it's not exactly a rigid rotor, but to a high degree of approximation, this is a rigid rotor. Similarly, many other diatomic molecules, they can be, approximated to the first degree at low temperature as rigid rotors, because the only at low temperature, the vibrational degrees of freedoms are not uh, available, but the rotational degrees of freedom become available at lower temperature. So we can construct the profiles, the energy profiles and energy diagram of these rigid rotor using the formalism that we already have. Because R is, fixed. So let's say the distance between this and this charge is D, which means that our potential energy, which we just wrote minus ZE square 4 pi epsilon R, is now just D, if this charge is ZE and this is E. But when we talk about the rigid rotor, it's better actually Q1 and this charge is Q2. So this is Q1, Q2, because then you can use it in a more general setting. So this is just a constant, because Q1 constant, Q3 constant, D constant. So everything is constant. It's better that we measure all energies with respect to this energy. And in that case, we can actually just take V to be 0, because when V is 0, essentially we are measuring all energies with respect to this potential, this constant potential energy. So if we take this V to be 0, then our differential equation essentially becomes only this part and times psi. And since our R is a constant, all these derivative would also will yield 0. So essentially our differential equation will just be H psi is equal to E psi, and H psi is E psi, and Hamiltonian is nothing but now just this L square over 2 mu R square, and R is D. So this becomes Hamiltonian is L square 2 mu D square, and this psi is just Y LM P Y LM theta phi. And this L square, when applies to this one, it gives us L into L plus 1, 2 mu D square, and we can then cancel YLM from both sides. So the energies of this rigid rotor, they're given by this spectrum. That at L is equal to 0, the energy is 0, and at L is equal to 1, there is this 1 into 2 over this 2 mu D square, where this D is just the distance between the two charges, and so on. So we can get this rotational energy spectrum of molecules simply by this equation. Any question regarding rigid rotor?
Sir, how have you operated on the right side of the equation?
Sorry, how is the operator what?
How have you operated on the right side of the equation?
So I haven't operated. This E is a scalar multiple. So this E just multiplies here. And after L square operates on here, I get L into L plus 1 multiplied by YLM. And then it's just a usual algebraic equation. So I just cancel YLM from both sides.
Okay. So
I can't cancel it here because this L square is an operator operating on this one. So, but once it's operate, oh sorry, there is an H cut square missing from here. And once this operates over here, then the operator is gone and I get this eigenvalue times YLM, and then I just cancel YLM from both sides. Okay, so let's get back to our hydrogen atom again. So now we have this V of R to put here, and our equation becomes
सर
Mhm.
सर आप एक दफा फिर से बता दें कि L स्क्वायर ओवर 2 म्यू D स्क्वायर का 1 ओवर 2 म्यू D स्क्वायर कहाँ से आ रहा था?
ये 1/2 म्यू डी स्क्वायर कहाँ से आया? ये आया है, ये देखें, ये है 2 म्यू आर स्क्वायर, एंड व्हेन आर इज इक्वल टू डी, सो दिस बिकम्स 1/2 म्यू डी स्क्वायर, एंड दिस
Where
टर्म
is the where is the remaining differential equation part?
so
V is equal to 0.
so since r is fixed is equal to d, r is not changing, which means that all these derivatives will yield 0. So they will now no longer be doing anything, because our psi is it has these two parts, and when this r is equal to d, so whenever you operate derivative with respect to something which is a constant, so this is just a constant then, so we wouldn't need this term in the Hamiltonian. Okay.
Okay, sir.
All right. Okay, so perfect. Let's now talk about hydrogen-like atom. Okay, just to give you an idea of what associated Legendre equations look like, let me copy them over here. This is just a table from the book. Let's see if it works. Let me copy again. It says it can't work. Okay, so just to give you an example, so this associated Legendre equation, so when L0 M0 is just a constant, when L1 and M0 it's cosine, and when L1 for both M plus minus 1 it's the same, and so on. So you can find all these Legendre equation in the book. Okay, so let's get back to the hydrogen atom now. So now we have V again minus ZE square 4 pi epsilon naught R, and we have our full equation minus H square 2 mu and partial square by partial R square plus 2 over R partial R plus L into L plus 1 H bar square 2 mu square R minus ZE square 4 pi epsilon naught R into psi is equal to E psi. Now, if I take E psi is equal to some function of R into YLM, then YLM will cancel from both sides, because there's no derivative on theta and phi, and we have already applied this operator. So this will reduce to only an equation in capital R. So this double derivative of R, let me write it R double prime, and this would be R prime plus L into L plus 1 2 mu R square minus ZE square 4 pi epsilon naught R, and let's bring this E to the left side, minus E into capital R is equal to 0. So this is the differential equation that we now have to solve to find capital R, which is a function of R, and this will also be function of L, as we can see that because L is appearing in this equation. And we have to solve this differential equation, and the conditions that our solutions should satisfy are these. The first thing is this: since we are going to use this R as part of our wave function times this YLM, so it means whatever the conditions have to be satisfied by psi have to be satisfied by R. And since this wave function is interpreted as representing probability through its mod square, because we know this psi mod square represents probabilities of finding the electron in some region. So it means that since the probabilities have to be finite, this R has to be finite everywhere. And also, so this is one condition, that R should be finite. Actually, more precisely, not R, but these probabilities have to be finite. And we'll see that what does it really mean. And the second thing is, since we know that the total probability has to be 1, so that the particle can be found somewhere with the 100% probability. So it means that this R has to be, R should go to 0 as R goes to infinity. Because if R doesn't go to 0 as R goes to infinity, then the total integral will not converge. When we will be trying to solve this integral over whole volume, for it to converge, this capital R has to go to 0 as R goes to infinity. So to make sure that these conditions are satisfied, the solution is assumed to be of this type, where there is some exponential term which decays as R goes to infinity, and there is since this is not an equation with constant coefficient, it can be solved using some series solution method. So it can have a solution like this, and where this is expanded at some series, and this series cannot go to infinity, because if it keeps on adding terms up to infinity, then this thing will not satisfy that as R goes to infinity, this R should be 0. So this has to end somewhere. And actually, you can see the argumentation in the book that this can end at n minus L plus 1, where n is any integer. So you choose n as some integer, and this L, which already comes in this differential equation, if you just stop at j is equal to this, then you can get a finite polynomial instead of an infinite series to represent solution of R. And more precisely, actually, the solution then is like this: R power L exponential minus Z over NA into R, and sum goes from J0 to N minus L plus 1 BJ RJ, where these coefficients are found to be related with each other through this recursion relation. J plus 1, J plus 2, L plus 2 into BJ, where this A is a constant given by 4 pi epsilon naught H bar square divided by mu E square. And the energies, they are found to be given by this minus z e square over 8 pi epsilon naught a. Okay, so this gives us the radial dependence of this function, and since it depends on n and l, it's usually written like this, r sub nl, function of r, because there's n and l involved, and this is a polynomial, as we can see, and the degree of the polynomial is n minus l plus 1. So if n is 1 and l is restricted to be 0, 1, all the way to n minus 1. So if whatever is the value of n, l has to be 1 less than that to make sure that this coefficient doesn't get negative, so that this r doesn't go to infinity. And also this n is an arbitrary integer. This can be anything. There's no restriction on n. It can be 1, it can be 1,000, it can be a million, anything. There's a restriction on l, however, that l will always remain 1 less than n. So this is a polynomial of degree n minus l plus 1, and the coefficients are related by this. The energies are given by this, and we can see that the energy is dependent on n only. It means that each energy level is a degenerate state, because L's can be different. So for each energy level, there are different values of L, and we actually haven't talked about it, but there's a degeneracy with respect to M as well, this YLM that we were talking about. So M is restricted to be from minus L all the way to L. So for each L, there are 2m plus 1 values of 2m plus 1 SLM functions available. So the total degeneracy is essentially then L into 2m plus 1, because for each n, there are L possible radial functions, and for each value of L, there are 2m plus 1 YLMs. So this is the degeneracy for each energy level. So for each value of n, there is these many, this is for each value of L, there are 2L plus 1 values of M. And if we can actually express it in terms of n instead of L. So for each value of n, there are n values of L, and so for each n, there are n values of L, and for each value of L, there are 2n plus 1 for each L. There are 2L plus 1 values of M, and so it becomes 2n plus 1 degeneracy for each n. Let me just see, into, is there an n as, so n into 2n plus 1. So for n is equal to 1, there is 1. For n is equal to 2, there is 4. For n is equal to 3, there has to be 2n square. 9, I think it comes out to n square. For each value of n, there should be n square possible values, and let's see how. For each n, there is n values of L, and for each value of L, there are 2L plus 1 values of M, So it should be I'm forgetting how to work it out, but I think for each value of n, there are n square degenerate values, which mean that for each value of n, there are these many possible wave functions. Okay, so it means that if we talk about the energies of this hydrogen-like atoms, it's like this. So for n1, we have a certain value of energy. So if you work it out, this is minus 3.6 electron volt, and for n is equal to 2, the value of energy is actually minus z. It's z square over n square E1. So you can use this thing. So this part is 13.6 electron volt. So we just keep multiplying with z square and dividing by n square to get all these energy levels. And I'm sure you all know how to get these energies out. And we can write the wave functions like this. So now the total wave function psi and Lm of r theta phi is given by r and L of r into YLM of theta and phi. And if you substitute the expressions for the YLM, it is R and L of R, SLM of theta phi exponential iota and phi. And so any questions so far? Okay, so let's now discuss these wave functions. Okay, and let's start from looking at this function RNN, because this is actually one of the most important part of this wave function, which tells us the distribution of probability as a function of radial distance from the nucleus. So this R and L of R polynomial. This has a polynomial. Actually, let me show you some of these functions. It's better to take a look on them. Okay, so let's see if it pastes it here. Perfect. So we see that we have this radial function for the case when psi is 100, and you see that its polynomial order is 0 because I don't see any r over here. So that coefficient bj that has been evaluated. So for n1 l0 m0, this function r10, this simply becomes, since this j is only 0, so b naught r power 0 is constant, and r power 0, this is also 1, so exponential minus z over n is 1, so minus z over a into r into b naught. So I have b naught exponential minus z over ar. So this is the radial part of the wave function. And we can find this B naught by normalizing. So the normalization requirement is this. Let me just state that. So we don't have to normalize this function, okay? We have to normalize the whole wave function. And the whole wave function normalization requirement is this, that the total probability over all volume, all space, this should be 1. And if we evaluate in spherical coordinates, so this becomes psi mod square r square sine theta d phi. So r goes from 0 to infinity, theta goes from 0 to pi, and phi goes from 0 to 2 pi. So this has to be 1, which means that if I now put for psi square as r square ylm square into r square sine theta d phi. Now we can separate the integral because theta phi dependence is only present in the spherical harmonic. So for r dependent part, there's a dr here, we can make it separate. So 0 to infinity r square small r square dr, and then I have integral over theta and phi y lm square sine theta d phi. But this is already normalized, so this gives us 1. So the normalization requirement for the radial part is this. So using this integral, we need to put this this r10 in there and find this value of b naught. And once we do that, we can find the radial part equal to this. Similarly, for the 2s part, where n is 2, l is 0, and m is 0, we can work it out, and we see that this will have a polynomial of degree 1 because this is r power 1. And then similarly, because n is 2 and l 0, so the highest power is n minus l plus 1. So n is 2 and l is 0, so 2 minus 1 is 1. So this is a polynomial of degree 1. So for this 2p, n is 2 and l 1. So again, this is a polynomial of degree. So this is L1, which means that it should be, so this R is actually coming from this part. It's not coming from that polynomial, it's coming from here. So R power 1. So we have something like this, RL into a polynomial of degree n minus L plus 1. So if we want to find out the zeros of this function, for example, I want to plot this function R as a function of R, and I want to see where it crosses, this 0 axis. I don't have to worry about this because this will always give me zeros at the origin. And to find the zeros that are not at the origin, we only need to have to worry about this polynomial m of R. And this is important because this radial distribution will give us the probability density distribution. So to work out where the that probability is 0, we only need to think about this this polynomial part, and we don't have to worry about this part. For this 3s, we have a polynomial of degree 2, and for 3p, we have a polynomial of degree 2, degree actually 1, and then this 1r is coming from outside, because there was r power 1 over here. Similarly for 3D and so on. Okay, let's just look at some of these radial functions and develop some understanding. So for that, let me plot a couple of them as a function of r. So R1s is something like this. Okay, because this is just an exponential function like this. And we can see that at r is equal to 0, it is some constant. So it's actually touching this axis somewhere. So let me start from here. So it's like this. And for another one, let's say for 2s, it is something like this. So this is 2s, and let's see how I can say that. So for 2s, it's like this. So it's a polynomial. So first of all, let's see what happens at r is equal to 0. At r is equal to 0, this is a constant. This is a 0. So I again have a constant. So at r is equal to 0, it starts at somewhere. But then it also has, it goes to 0 at r infinity, because when r is equal to infinity, this term goes to 0. Even though at r is equal to infinity, this term increases, but this exponential term goes to infinity much faster than this term. Because if you know, the exponential actually has, lot of terms like this, x squared, and so on. So there are, higher powers. So this goes to 0 faster than this r goes to infinity. So the product as a whole goes to 0 as r goes to 0. So this part is fine, that r goes to 0 as at infinity. And we can see that somewhere in between there is a 0 as well, because if I put it equal to 0, I can solve it for 1 minus zr over 2a is equal to 0, which will give me r is equal to 2a over z. So there is a 0 of this function at this value of r. So that's why you see that it crosses this r axis at a certain point. Similarly, if we think about 2p, 2p has a plot like this. Okay, and we can see from here, you see at r is equal to 0, this is 0 because there's a r multiplying. And at r infinity, this is again 0. And same argument, because this exponential goes to 0 faster than this r goes to infinity at r infinity. And there's no 0 in between. If you look at 3s, 3s will have two zeros in between r is equal to 0 and r is equal to infinity, because this is a second order polynomial. Does everybody understand that a second order polynomial will have two zeros? Good. So it means 2p will have, 3s will have a plot like this. So it is 0 here. So which one we were talking about? So this is 3s. So where is 2s? So this was 2s, 2p, 3s. So 3s has two zeros. So 2s, so this was 2p, and 3s would be something like this. Something like this. Because there are two zeros, one over here and one over here. So let's see the probability distributions. Because this was just the radial function, but let's now see r square, because this is proportional to the probability distribution. So now we have to first multiply with r square and then take square of r and then plot. Now for 1s, this becomes like this. Now you see 1s was non-zero at 0, the radial distribution function, but the probability is 0 over here simply because of this r square multiplying. And it has a maxima somewhere, and this maxima actually can be found that it is exactly equal to r is equal to a. So that's why this A is also referred to as the Bohr radius, because for 1s orbital, the probability of finding the electron is maximum at r is equal to A. And I hope that this also clarifies if any of you still has any misconception about what we mean by electrons in orbitals. You know, when we really draw a circle, and that's initially, you know, we tell students in high school that, okay, electron is going around. But as we go up, we realize that it's, you know, not possible to really specify the trajectory of electron. All we can do is talk about the probability of finding it somewhere. So for 1s orbital, actually electron can be found anywhere from r is equal to 0 to infinity. The only thing is this, it has a maxima somewhere over here at a distance of r is equal to A, where the probability of finding it is maximum, but it can still be found small at a distance smaller than A and at a distance larger than A. Okay. So for 2p, if we plot r square for 2p, it is something like this. So this is similar in shape almost to the 1s orbital, but it's, you know, the maxima lies a little bit, you know, farther than the 1s orbital. Now let's talk about the 2s. For the 2s, since it's non-zero before it here, as so the 2s is something like this. So it has a probability density. Actually, I didn't draw it really well. It is something like this. This is smaller, and then this is larger, and then so this is 2s. So 2s has a probability of being found actually closer to nucleus as well than even the maxima of 1s. But this is really very small. Most of, you know, the chances for finding it are farther than the 1s orbital. But this maxima is actually even nearer than 2p orbital. So that's why when the electron goes to an excited state, the 2s state is likely to be filled before the 2p state, because this one a little bit smaller than the 1s one. Similarly, you can find orbitals for higher energy states, and you see that the radial probability distribution really gives us a view of how to imagine the presence of electron around the nucleus. And this then later on helps us in understanding different bonds and different molecular properties of the atoms as well. Any questions so far? Okay, if not, go ahead.
सर तो आपने लास्ट बात की है रेडियस वाली 2p और 2s के बारे में, वो एक बार रिपीट कर दें।
जी, मैं ये कह रहा था कि अगर हम इनकी प्रोबेबिलिटी डेंसिटी ड्रॉ करें तो एक्चुअली जो 2s का मैक्सिमा है वो जो 2p का मैक्सिमा है उससे करीब है न्यूक्लियस के. द न्यूक्लियस इज प्रेजेंट ओवर हियर at r is equal to 0. So that's why 2s is more likely to be filled before 2p.
Okay, got it.
Okay. All right. So let me now talk about another important thing, which, you know, is sometimes overlooked in physics courses, but we will now need to really understand it because we will go on to molecular physics as well later on. And this is the what we call real hydrogen-like wave function. So far, we talked about this psi, okay, which is just described by NLM, that we can have psi 100, psi 200, psi 210, psi2 1 minus 1, psi2 1 plus 1, and so on, where the third index tells us the value of m, the second value of L, and the first value of n. But I will just discuss their symmetries later on, but we will see when we go to molecular physics that instead of these orbitals, the real hydrogen-like orbitals are actually more useful in describing the bonds, because they have those symmetries that we require to express the bonds in molecules. And there's no, mathematical restrictions on us to choose the size in this specific values only. And the reason is this, that we already know that if we have, let's say, some functions f1, f2, etc., which are eigenfunctions of some operator. So if these, which are solutions of some differential equation, if this is, f1, f2, f3, etc., are a solution of a differential equation, we know that any linear combination would also be a solution of the same differential equation. So if f1, f2, f3 are solution of the Schrodinger wave equation for hydrogen, then any linear combination of these solutions is also a solution of the differential of the same differential equation. So it means that we not only can use these NLM solutions to represent the solutions of Schrodinger equation, but we can also use any linear combination of them to represent the solution of the differential equation as well. And so that's why there is another construction of these wave functions other than the NLM construction of wave functions, and let's talk about them as well. And let me start from 1s orbital. So for 1s, the m is 0. So if m is 0, the wave function psi 1 0 0, which we represent with psi 1s, or sometime, actually most of the time, we will just call it 1s. Okay, so this is a real wave function anyway. And you remember why? Because the imaginary part comes only from this factor iota m phi in exponential in the ylm. So if m is 0, then this part isn't present. So it means that this is, a real function anyway. Similarly, for 2s, m is 0 again. So psi 2 0 0 or psi 2s, or we will simply call it a 2s orbital. This is a real orbital already. So let's construct, let's look at 2p. So for 2p, we have three situations. We can have 2p 0, we can have 2p 1, or we can have 2p minus 1, right? So 2p 0 mean NLM is 2 0 0, no, 2 1 0, and 2 1 1, and 2 1 minus 1. So n is 2, but L is m is 0 for 2p 0, and m is 1 for 2p 1, and m is minus 1 for 2p minus 1. So we can use wave functions described by them as well, but this is a real wave function because m is 0, but this is a complex one and this is a complex one. So let's use these complex wave functions to construct two real wave functions, and we can easily do that because this has a factor iota phi and this has a factor minus iota phi, and everything else is exactly the same in both of these functions because n is 2, n is 2, L is 1, L is 1. And the associated Legendre polynomials, they are independent of the sign of m. So the SLM part is exactly the same in both of them because these SLMs are independent of the sign of m. Now we can construct the 2p, what we call 2px orbital, or you can represent it sign, I don't know, 2 1 x, and this is just the linear combination of 2p1 and 2p minus 1. Because if I add both of these functions, what will happen? This has exponential iota phi and this has exponential minus iota phi. Everything else is common. So this exponential iota phi plus exponential minus iota phi over under root 2 will give me cosine, and this I have to put to, to keep the normalized. So this will give me 2 cosine phi. So everything into cosine phi. Similarly, we can construct 2py as 1 over under root 2, 2p1 minus 2p minus 1. So there has to be so there has to be an iota over here, because when I make exponential iota phi minus exponential minus iota phi, there will be an iota sine phi. So this will have a term sine phi and iota will go away. Similarly, if we have d orbitals, so d orbitals come with L is equal to 2, which means m can be minus 2, minus 1, 0, 1, and 2. So this one is called, this one is already real, and this is given a sign d, I think z square. And by combining these two, we can prepare two more real wave functions. And by combining these two, we can prepare two more real wave functions. Okay. And I will explain the nomenclature for them now. So let's see. The 3D xz is 3d1 plus 3d minus 1. So if you combine, if you add these two, the resulting orbital is called 3dxz. And if you subtract, it's called yz. And it's 3d1 minus 3d minus 1 over iota. Similarly, if we take the 3d2 and 3d minus 2, this orbital is called 3d x square minus y square. And if we subtract them, this orbital is called 3d xy. And let me explain you why this is called so, but let me first paste the orbitals here so we can discuss these signs. Okay, so if you see, so this is already real. Similarly, 2s is already real. This 2pz is exactly the same as 2p0, but this 2px, which was combined, which was obtained by 2p1 plus 2p minus 1, if you see, this has this term r sine theta cos phi, and we know that this x is equal to r sine theta cos phi and y is equal to r sine theta sine phi and z is equal to r cos theta. If you recall, this construction, that if there is radial vector of angle theta and phi, this component is called r cos theta. And when you take its projection over here, this is r sine theta. So x component is r sine theta into cos phi, and y component is r sine theta into sine phi. So this sine phi is y, cos phi is x, and cos theta is. Now this r sine theta cos phi is actually x. So it means that this 2px wave function now only depend on x. Similarly, this 2py wave function, which is obtained by subtracting 2p1 and 2p minus 1, it has this term r sine theta sine phi, which is y. So that's why it's called 2py. This 3s was already real. This is nothing but 3s orbital. This 3pz again has, you know, this z dependence, and this is actually just 3p0. 3px again have r sine theta cos phi, and 3py have again r sine theta sine phi dependence. This 3d z square is actually just 3d 0, and it has this factor r square into cos square theta, which is just z square. So that's why it's called the z square. And this, you know, 3dxz, which we obtained by, I think 3dxz, we got it from 3d1 plus 3d minus 1. So it has this r square into sine theta cos phi. So 1r sine theta and cos phi is x, and the z is r cos theta. Similarly, this yz is r square sine theta cos theta sine phi, so it depends on only the product of yz. Similarly, if you work out x square minus y square, this actually is this r square sine square cos 2 phi, and xy is nothing but r square sine 2 phi. So these, you know, the symbols that are here, they will also later on help us to understand the symmetries and their graphs. But the labeling comes from this fact that it indicates the dependence of these orbitals on the spatial coordinates x, y, z, etc. Okay. Any question about the labeling? Perfect. So let's now do the last thing that we want to understand these orbitals, and that is how to visualize these orbitals. Okay, and to visualize these orbitals, we see that we have to work out this thing. This is actually the total probability of finding the particle in a small, you know, spherical volume region. So when we have to work out to visualize or to plot them, we actually have to work out this with this function. So just to expand this psi square, so this psi mod square is actually r square ylm square sine theta. And by the way, but right now it's not ylm square, because for these real wave functions, this we have, you know, taken the linear combinations. So this psi mod square is now a combination of these ylms, because we have added and subtracted the same the same and opposite sign m. So let's just work out with this, you know, psi mod square as well. So essentially we have to work out with this function psi mod square r square sine theta. And we see that this is, you know, a function of really r, theta, and phi. And since this is the probability, if we want to really plot it, we have to work in 4-dimensional space, where we can compute probability as a function of these 3 dimensions. So the 4th dimension would be required to plot this p, which is of course not possible. So people have, you know, devised ways to visualize these orbitals. And actually, it's an important part. So let's, keep it for the next lecture, and we will discuss the plots of these wave functions in the next one. I don't want to rush it. Any question regarding this?
सर मेरा पीछे से एक सवाल था
Mm-hmm.
सर आपने m जहाँ पे 0 है वहाँ पे हम लिनियर सुपरपोजिशन नहीं बना रहे, लेकिन जहाँ पे m की वैल्यूज 1 और -1 है वहाँ पे हम सुपरपोजिशंस बना रहे हैं, तो
जी, जी।
वो थोड़ा सा कंफ्यूजिंग लगा है, अगर वो एक्सप्लेन कर दें।
जी जी। तो जो अभी फिलहाल जो है वो हम ये कह रहे थे कि वी वर ट्राइंग टू कंस्ट्रक्ट रियल वेव फंक्शंस। तो जो m0 वाले हैं वो सारे रियल हैं ऑलरेडी, और जिनमें m नॉन जीरो है वो सारे कॉम्प्लेक्स हैं, क्योंकि सब में जो YLM है उनमें फैक्टर आता है एक्सपोनेंशियल आयोटा m5। तो व्हेन m इज 0, जो कॉम्प्लेक्स फैक्टर है वो वैसे ही खत्म हो जाता है। सो द रिमेनिंग फंक्शन इज रियल।
और तो सर सुपरपोजिशन से वो रियल हो जाएगा?
हाँ, क्योंकि जो एक्सपोनेंशियल आयोटा फाई और अगर आप एक्सपोनेंशियल माइनस आयोटा फाई को ऐड करें तो आपको पता है ना कि जो इमेजिनरी पार्ट है वो कैंसिल हो जाएगा एंड वी विल गेट cos फाई।
ओके सर, थैंक यू।
सो और अगर सब्ट्रैक्ट करेंगे तो आता है आयोटा साइन फाई, लेकिन हम फिर वो सुपरपोजिशन में नीचे आयोटा जब माइनस करते हैं तो नीचे आयोटा से डिवाइड कर देते हैं।
ठीक है सर, समझा।
Okay, but the real reason will be apparent when we work out their graphs, क्योंकि there's no point in constructing real functions. Zara physicists, chemists सारे जो हैं वो they can work with complex wave function as well, no problem at all. But we'll see that these real wave functions have certain properties that would be helpful. वो सही पता तो चलेगा जब हम molecular bonds को study करेंगे, but you'll be able to get the idea from when we study their graphs. Okay.